Good morning everyone. Today we see the design of one-way slab and design example. Myself, Dr. J. Sagaruvan, Professor and Head, Department of Civil Engineering, Rohini College of Engineering and Technology. The one-way slab. One-way slab is the slab which is supported by beams on two opposite sides to carry the load along one direction. The ratio of longer span by shorter span is greater than or equal to 2 is considered as one-way slab because the slab is bent in one direction, in the direction of the shorter span. So the Ly by Lx greater than or equal to 2. Let us see a design example of one-way slab. Okay, design a simply supported one-way slab over a clear span of 3.5 meter. It carries a live load of 4 kN per meter square and the floor finish of 1.5 kN per meter square. The width of the support wall is 230 mm. Adapt M20 concrete and Fe415 steel. First of all, to determine the depth of the slab or thickness of the slab, let us assume the approximate depth, that is span by depth, is equal to 26. From that we have to find out the value of D is equal to 3500 divided by 26, that will be is equal to 134 mm. Assume the overall depth is 160 mm. So the clear cover 15 mm for a mild exposure. So small d, normally we have to take it as 160 minus 25, so 140 mm. Next we have to find out the effective span of the slab. Normally the effective span is least of the following. First one is L is equal to span length, that is a clear span, 3.5 plus width of the support, that is 230 divided by 2 plus 230 divided by 2. So we will get a value of 3.5 plus 0.23. So that will be is equal to 3.73. Then effective length L is equal to 3.5 plus the depth of, that is the effective depth of the slab, that is 0.14, 3.64. So the least we have to take it as a effective length. So 3.64 meter is the effective length of the slab. So the effective length L effect is equal to 3.64. Next, load on the slab. So we have to determine the load one by one. First of all, the self weight of the slab. Thickness of the slab already we find out 160 mm. So 0.16 into 25 will get 4 kilonewton per meter square. Next is the live load given in the problem as 4 kN per meter square. Floor finish we have to take it as 1.50 kN per meter square. So add all the load like self weight 4, live load 4 plus floor finish, that will get 9.5 kN per meter square. So ultimate load we have to determine by 9.5 into 1.5. So that will be equal to 14.25 kN per meter square. Next we have to find out the design bending moment and check whether the given depth is enough to carry that bending moment. So first we have to find out the bending moment. M is equal to WL square by 8. Substitute the value of W of 14.25 into 3.64 square divided by 8. So that will be equal to 23.60 kN per meter. So minimum depth for this moment we have to calculate mu is equal to 0.138 FCK into BD square. So from we have to determine D is equal to square root of mu divided by 0.138 FCK into B. So substitute all the values here. Finally, you will get a value of 92.4. That is more than, that is less than what we are provided. So for this moment, we require only 92.4 mm depth, but already we provided 140 mm. Hence, this depth is enough to carry this moment. So hence this is safe. So based on the moment, given moment and the depth, we have to design an area of steel reinforcement. So as you know, AST we have to find out using this relation. mu is equal to 0.87 Fi AST into D, 1 minus AST Fi divided by FCK into B into D. So substitute all the values here and simplify. Finally we will get a value of AST is equal to 504 mm square. So for the AST, for main reinforcement we have to use a 10 mm diameter bar. So spacing calculation, spacing SV is equal to small AST divided by capital AST into 1000. Small AST we have to calculate by pi d square by 4, that is pi into 10 square divided by 4 divided by AST 505 into 1000. So SV is equal to 154 mm. So provide 10 mm diameter rod at 150 mm center to center. Next we have to find out the distribution star. That is 0.12 percentage of total grass area. So 0.12 divided by 100 into 1000 into 160 will get a value of 192 mm square. So distribution, we provide 8 mm diameter rod. So spacing of 8 mm given by 50 divided by 192 into 1000. 50 pi d square by 4. Okay, the value of 50 is pi d square by 4. So we will get a value of 260 mm. So provide 8 mm diameter rod at 260 mm for a distribution reinforcement. So 10 mm at 150 mm center to center for main reinforcement, or for a distribution provide 8 mm at 260 mm center to center. Next we check the shear. So descent shear we have to calculate by WL by 2. So W we know 14.25 into 3.64 divided by 2, 25.93. So from that we have to find out the tau V. Tau V is equal to VU by B into D. So tau V we will get 0.18 Newton per mm square. So tau C max also we will take table 20, we are getting 28 Newton per mm square. So just to check the tau C value by determining percentage of steel reinforcement, that is 0.37, that is percentage of steel reinforcement. From we have to find out the tau C value is 0.42 from IS 456 2000. Here the tau C is greater than tau V, hence the shear check also okay. Finally check for deflection. The check for deflection normally L by D, actual L by D is less than allowable L by D. So allowable L by D we have to find out by L by D basic into modification factor. If the span exceeds 10 meter, that K1 value, that is modification factor, we have to find out 1.38. For a percentage of steel reinforcement that is 0.37. So L by allowable is equal to modification factor is 1.38 into base span by depth basic value is 20. So we will get a value of 27.6. The L by D actual value is 25.92. So that actual L by D is less than allowable, hence the deflection also okay. So this is all about the design of one-way slab. Thank you so much.